Okay, so volume. Finally, volume. Okay. We're going to do volume two different ways. One is working with what are called cross sections, and another way is when you take like a base and you rotate it and you get a solid of revolution. So first of all, let's start with the definition. It's just the integral of area. So think about like if you're taking I was going to say like a sphere. Do you guys remember the surface area of a sphere or the volume of a sphere?
The 3r squared.
Well, yeah, so what's the volume of a sphere? 4/3 pi r cubed. Do you remember what the surface area is? 4 pi r squared. It's okay if you don't remember it. They would be given to you. So think about this. If I do the derivative of volume, I get surface area. If I integrate the surface area, I get volume. Okay? So, but now we're going to extend that to the area of any shape. Okay? So let's start with cross sections. Okay? So I'm going to show you what that looks like with this. Oops. Hold on, I need my mouse to do this. Okay, so I'm going to show you the idea. Okay, I know it's a little crooked here, but let's imagine that we have a region. This is the x-axis, this is the y-axis. The upper curve is this red one, and the lower curve is the blue one. Okay, so first thing we want to look at is a typical cross-section. So if we imagine, right, if we were to draw from the top curve to the bottom curve, that's the length of the cross-section. Now, these cross-sections can be any type of shape. They could be a square, they can be a triangle, could be a rectangle, could be a semicircle. So imagine, here I'm going to try to show. So there's our base, and let's say we want to put a square in that base. And then, let's say, right, so depending on where that square is going to change the dimensions of it. Do you see that? Now let's add in more of those. Okay, so you can kind of see this shape, this solid, right? That's with 14. Here we have, it only gets to 100 of them, right? So you can kind of see what this shape looks like. And imagine if there's infinitely many of these. Okay, now we can change that to triangles. So now how does that shape look? Okay, a little bit different. And we could do semicircles. So now it's more rounded. Okay, so the idea is figure out what are the dimensions for one cross section, and then we're going to integrate that, right, over whatever interval we have here. Okay, so I like to show you that visual because it's really hard to picture when you're first doing them. So now we'll go back and we'll go through the steps, and then we'll do an example you can see at the bottom there. Okay, so a typical cross section, and that could be, just a reminder, it could be a square, it could be a rectangle, it could be a triangle. Now that triangle could be equilateral, it could be an isosceles right triangle. Those are the typical ones. Could be a semicircle. It could even be a circle. Okay. Those are typically the ones that we have to deal with. Okay, you should know those formulas, right? We should know the formula for a semicircle. We should know the formula for a triangle, because that's the second step, right? What is it, base times height divided by 2, or is it going to be 1/2 pi r squared? So again, the cross section, when they're perpendicular to the x-axis, the length, so remember when I first showed you that line segment, what was that dimension? It was just the top minus the bottom. If it's perpendicular to the y-axis, we would do right minus left. That should look familiar and similar to when we did the area between the two curves. Next, we find the limits of integration, and finally integrate. Okay, so here, okay, what do we see? We see two curves. It's negative root x and positive root x, or here it's labeled as x equals y squared. Okay, so we have this solid lies between the planes perpendicular to the x-axis. That's important. Okay, if it was perpendicular to the y-axis, we would have to change things a little bit. This would be from 0 to 4. Those are going to be our limits of integration. And we're going to do squares with bases in the xy plane. That's important. Sometimes they'll give you a square with the diagonal in the xy plane, and then that will change the way we evaluate it. Okay? All right, so let's find a formula for the area of one cross section, and then we'll use that to find the volume. Okay, so let's do cross section length first. Okay, this is right here, that's our base. So when we think of the base, that's our 2-dimension, and then we want to work with that to come up with a formula. So if I were to go from root x to negative root x, what's the length of one cross section? 2 root x. Right? Root x minus negative root x gives us 2 root x. Okay, so you see here these little lines. These are like typical cross-section lengths. And then what we want to picture is these squares that come like out of the board, if you will. So what would be the area of one of those squares? Yeah, because it would be 2 root x times 2 root x, or 2 root x squared. So that would be 4x. Right. Again, you're picturing like one square has these dimensions. And again, the squares are going to be smaller, obviously, when they're closer to the origin. And then they're going to get bigger as they get further away, right? Make sense? Okay. Last, we're going to do the volume. So we want to integrate what? 4x, the area, dx. And what are the limits? Good. Okay, so what do we get? 4x squared over 2x squared. Evaluated from 0 to 4. What do we get? 32. Good, yes.
But I just don't understand how integrating the area of one of these squares.
You're not integrating one of these squares. You're integrating, when you're integrating, you're finding infinitely many of those.
So why did, because we only worked with one of them from.
Okay, but
They're all 4x. Oh, wait. Oh,
they're all 4x. They're all 4x, and remember, your dx.
I got it.
Okay, you got it? You sure?
Because everyone's 4x.
What's that?
How are they all 4x?
So what's,
I get it, actually.
like when x is 2, what would the area of that square be? It would be 8x. What would be when it's 4? It would be 16. Okay. The formula stays the same, but the x is what changes, and that's what, when you have your limits of integration from 0 to 4, that's how it takes care of it. Okay. All right, same base as example 1. So this time we want to go with semicircles with diameters in the xy plane. Okay, so what that means, so again, I'll just kind of draw the, oh, that's kind of messy, but it doesn't have to be perfect. All right, so here's our Still same thing, square root of x to square root of negative x. But this time, if you can imagine, and again, it's kind of hard to draw here. Here's your cross section, and then imagine there's like semicircles coming. Like this is flat, and the semicircles are coming out of the board. Picture that? Okay. And specifically, the diameters are in the XY plane. So now the cross-section length is still the same, right? We said the cross-section length is still 2 root x. But this represents the diameter. Okay, so same question. We want to come up with an area formula of one cross-section and then find the volume. Okay. So if there's some, so if the diameter is 2 root x, then the radius would be just root x. And we need that because the area is, good. So a of x is 1/2 pi radius squared. So it's just going to be what? Half pi x. Good. And now the volume. Limits of integration are going to be the same, so 0 to 4. Now, also I'm just going to put the 1/2 and the pi out in front. You don't have to. But coefficients don't change anything, right? Okay. So that's just going to give us what? X squared over 2, so then that'll be pi over 4 x squared. Right? And then what do we get? So this would be x squared over 2, so I just combined it to make it over 4, and just, it doesn't really matter how you, plug in 4, we get 16 pi over 4, or 4 pi. And you don't need to worry about units, okay? It's just going to be implied, only if it's like a word problem where they give you units, otherwise you can just leave it. I mean, it is. Were there words? Yeah, a lot of them. But again, if the thing about word problems, and I try to do this specifically for, like, these aren't necessarily spelled out in your book. I mean, this is part of my explaining to you to come up with like a system, right? A step-by-step process to break those word problems down into something more manageable, right? So now when we get to a different problem, we can think back to those steps. Good? Okay, so a solid lies between planes perpendicular to the x-axis. Okay, so again, anytime you see perpendicular to the x-axis, everything has to be in terms of x. If it said perpendicular to the y-axis, we have to do everything in terms of y. And, they already gave us the limits, -2 to 2. They gave us the cross sections this time are isosceles right triangles with the bases in the xy plane. Okay, that's going to change things. Yeah. And it's a semicircle. So let's just draw first. Again, I'm a visual learner, so I tend to teach that way. That doesn't matter. Okay, so it's a semicircle with radius 2.
Is it ever going to be like not the base of the triangle? Like could be a different part of it? Or is it usually could it be the height? Yeah.
What do you mean?
Because like could it be the height that's because it says like with bases in the plane.
Yeah. So so the base of an isosceles right triangle would be one of the legs instead of the hypotenuse. Okay, so let me.
So would the hypotenuse ever be like what we're basing it on?
It could be. It could be. So here, you're picturing the cross-section length, which is just going to be the square root of 4 minus x squared, right? Minus 0. So now imagine an isosceles right triangle with, right, this base is the same as this base. So that is 4 minus x squared. Well, if it's isosceles, the base and the height are the same, right? So this is going to be 4 minus x squared as well. Okay, so same directions, find a formula for the area, and then use it to find the volume. So area is going to be what?
4 minus x squared divided by 2.
Good. Right, makes sense. So that's how we get the 4 minus x squared over 2. And now volume. Now, quick note. I could put limits of integration from -2 to 2. However, it's much easier to double the area from 0 to 2. You don't have to do this, but I strongly encourage you. It will be much faster, right? It's easier to plug in 0 than to have to plug in 2 and then plug in -2 and subtract them. Does that make sense?
You can do it whenever it's symmetrical.
Whenever it's symmetrical. With area or volume, you can always double it. And sometimes, like on the multiple choice, they'll say, oh, which integral represents the volume? They might only have one that has a double in front, so you have to interpret that anyway. It's only with symmetry, though, right? It's got to be symmetrical. So I will have, let's see if we can do this. By hand. Right. Yeah.
Could you have also taken out the 2 from the bottom of the 4 minus x squared? Now that we have the 2 in the beginning, and then cancel them out.
Wait, which one?
Like, because it's 4 minus x squared over 2. So could you take the
Oh, and multiply it through so you don't have to deal with a
like,
fraction?
take out the 1/2 and put it on the left side, and then just
Yeah, you can do that. Yeah, it should all work. So this would be 2x minus x cubed over 6. Yeah. Yeah, that 2 in front, like you can multiply, you could take the 1/2 out, like all of those are just coefficients. Okay, what happens when we plug in 2? Save time. See, now that I have we could have done that though, right? Yeah. Okay. Of course. Yeah. The integral part? The 2 outside? Oh, so this has symmetry. So rather than going from -2 to 2, it's easier to have 0 as one of my limits of integration. So whenever I have symmetry, I always like to rewrite it this way. You don't have to, but notice it's a lot easier to how easy is it to plug in 0? You just get 0, right? So, okay. All right, now we're going to do rotations. Okay, so circular cross sections. This is when all of the cross sections are circles. So we're not working with triangles, squares, any of those other shapes. So cross sections are circular. These are called solids of revolution. So how do you find the area of a circle? Pi r squared. What is r equal to? Our function. Okay, so our area is always going to be pi times whatever our function is squared. So that means here's our formula for the volume. So actually these are a bit easier because it's just going to be whatever the function is, right, squared times pi. So here we have a region, 2 plus x cosine x, and so this is our base. And now imagine that we just start rotating the whole base. So you have infinitely many of these circles, so you get that weird, I don't know, shape. Can you, what's that? Like, looks like a what? Like a goldfish? Okay. So, okay, this here is our radius, okay? So when I'm doing the volume, now it's the integral of pi r squared, but again, with pi, it's just a coefficient. We'll throw that in front. From -2 to 2. Now this one I cannot double. You can clearly see that we don't have that symmetry that we had on the last problem. So I can't, right, I have to keep them the same. I have to keep it from -2 to 2. And can we integrate this by hand?
I think we can.
So the problem is the x cosine. Well, you can in Calc BC, but we don't have a method for taking apart this x cosine x. So we're going to have to just use a calculator for this. Oh, thank you. I forgot my squared. Good catch. Okay, so this is a calculator problem. Just a heads up, all the problems on the test are calculator okay. So most of it is going to be show me the setup and then plug it into the calculator. And then there will be a number of problems that it's just write the integral.
What constitutes a setup? Is this setup?
This is setup.
So you don't actually have to integrate?
You don't have to do anything by hand on this one. You can't
This
anyway.
one,
Yeah.
But even on the practice quiz, since it was calculator okay, I still like wrote.
Yeah.
out
Yeah,
that
that's
I didn't
okay.
know what you expected.
You showed extra steps just in case.
Yeah.
That's fine. All right. Did anybody? Also, just a quick tip. If you ever end up with a negative, then we did something wrong. Did you get 52? It should be in radians. Are you in radians? 0.429?
I got 25 points. That's what I got. 1, 3.
Oh, did we square it?
No.
Okay, hold on.
Did you also not? Yeah.
Oh, did we forget something?
Yeah, I think we got this right.
Now you got this answer? Okay, good.
And you said we don't need any use it.
No.
So that number is the
That's
volume
the-
of
of- That's the volume of this whole thing. So obviously, like if you think of how this could be applied in like real world examples, like you could come up with the function of anything and then come up with how much can that container hold, right? It can be an irregular shape. Obviously, we have formulas to figure out volume of cylinders and of cubes and cones, but now this allows us to find the volume of anything.
You have to know the equation.
You would need to know the function itself.
Okay.
Yeah.
But it can be like
Yeah. Okay. Question? I don't, Molly. We talked about this already. My husband got my son. Yeah, she does. Okay. Now, this last one, notice the base was the x-axis. Okay, but what happens if I have another curve and now I just want this part of it? Okay. You don't have to. I was just saying, like, what if? What you end up happening is what we call a disc or a washer. It's, or like a donut, if you will. So this is when you have two functions. All right. So now you have two different functions where you have an outside and an inside function. So think about the area, just like you did the curves, right? Remember when it was the region bounded between the two curves, you did the top minus the bottom? Same thing here, but it's going to be pi r squared minus pi r squared. Just keep in mind, R is always, when it says outside, it means the one that's further away, or the top one, minus the bottom one. And then here's our volume formula. So this is, R is always the furthest away from the axis of rotation. R is the closest to the axis of rotation. Today we're just going to do rotations about the X and the Y axis. Tomorrow we will do different lines of rotation. It is. It's, again, if you follow the step-by-step process, it's really not that, like, you think back to like related rates or some of those other problems, those are much more difficult. When we get to the volume, as long as you can, again, understand the process and what you're actually, like, what are we looking for? So here we have, okay, first quadrant, enclosed by the y-axis and the graphs of y equals cosine and sine. Bless you. And it's revolved about the x-axis. So here's the base, so to speak. And now here's what it looks like rotated. So you kind of have like this open area inside. Or okay, so first we have to figure out,
What's the pink?
that's a sample cross-section. Do you see the pink disc? That's a sample cross-section. So the cross-section is going to consist of the outer curve and the inner curve. Yeah. Usually what I like to do, so I figure out which one is big R, which one is little r. What do you think? Yeah, which one is on top? That's got to be the cosine. All right, this one's cosine. And this one is sine. Again, this is really zoomed in, by the way. That's why they look like straight lines. They're not, they're curved. So big R is going to be cosine. Little r is sine x. Okay, this time, what did we not give? Limits of integration. Now, first quadrant means my lower limit of integration is going to be just 0, right? So I have to figure out what that point is. Well, that's when sine and cosine are equal to each other, right? So when is that? That's a pi over 4. Okay, so volume. Again, pi on the outside, 0 to pi over 4. What are we going to have? Cosine squared minus sine squared dx. Yeah. Oh, just because it's easier to deal with later. You don't have to. So see it here above? It's pi big R squared minus pi little r squared. But I always put the pi on the outside. Just, it's easier to type in rather than having to type it in twice. Okay, can we integrate this by hand? No, so we're going to use a calculator for this.
I don't, wait, why can't we? We don't know how to like product it.
You could try u substitution, but you would need a sine attached to this and a cosine attached to this somehow. Yeah, but you still can't. You could try trig identities, but you're not going to need to do that. What do we get? Well, and then sometimes, like, I don't multiply the pi. If you just multiply or put this in, you get a half. So if you just type in from 0 to pi over 4, that part, you'll get a half. So the answer is pi over 2. Or you could write it as, everything on the test can also just be, unless I specify that I want it in exact form, everything's to 3 decimal places. Okay, good. All right, this, what? Yeah. Okay, volumes. So let's go ahead and graph. So it says y equals 2x. So this line might be better. Y equals x. And x equals 1. I know. Sorry, this is y equals, so this one's y equals 2x. This one's y equals x. And we have x equals 1. So we get this little triangular region here. No? Did we see it? X equals 1 is a vertical line. So you should end up with a triangle with these 3 vertices. Good. Okay, now, what do we want to do? We want to rotate this, so we're revolving that region about the x-axis. So kind of picture, if you were to kind of duplicate this on the other side. So it's going to end up almost like a cone shape, but it's scooped out, if you will, on its side. Sure.
So is that perpendicular?
Yes, because, okay, so anytime it says it's being rotated about the x-axis, that means the cross-sections are perpendicular to, right? Picture a circle that is perpendicular to the x-axis. Actually, a circle cut out, right? It's a washer. So what's big R? What's the outer curve? 2x? What's the smaller one? X? Okay, so the volume is going to be pi. What are our limits of integration? 0 to 1. Oh, sorry, I put y, I meant to write x. So then it's going to be 2x squared minus x squared. So this would just be 3x squared, right? Just if we, again, you have your calculators, but some of these are almost faster to just do by hand rather than having to type it all in. What happens when we do 3x squared? It just becomes x cubed. So pi. Yeah, that was faster to do, in my opinion, rather than even having to plug. But you have your calculator, plug it in, you can confirm that. So the volume of this shape is pi. Think about it though for a second. Really, you have an outside cone and an inside cone is removed from that. So it makes sense that a multiple of pi would be the difference.
And you disregard x equals 1 because that's kind of just like...
X equals 1 just helped us find the upper limit of integration. Oh. Uh-oh. Oh. I wasn't in. Okay, good. I always worry when I see like people taking pictures in the middle of class. Yeah. No. It's a long lesson. We're going to do...
Where we get things around other than x and y axis. I know. Are we stopping?
We're stopping when we get to that.
We put the H.
It's all good. Okay. So this last, yeah, we're stopping after this page, so we're fine. Okay. This is the exact same. So for this example, I'm using the same 2 curves. For the top one, I want to look at what's the volume when we rotate it about the x-axis. And then this one, we're going to rotate it about the y-axis. Okay? So, right, let's identify the top one is root x and the bottom one is a half x. And then, again, you don't have to duplicate it, but if it helps, right, kind of looking at rotating it is going to give you like this rounded solid with a cone cut out, if you will. Okay, so what's big R? Root x. And little r, 1/2 x. So the volume is going to be pi. What are the limits of integration? Where do these two intersect? Yeah, and if you're not sure, literally, you could just set them equal to each other, right? And solve, and you get 4. 0 and 4, right? Because they intersect at 0. And then it's going to be root x squared minus 1/2 x squared dx. Sure, use a calculator. You could do this one by hand. This one also was pretty easy. Huh? Nothing? Don't you think? Sometimes it's easier just to do it by hand rather. Oh, the one that's further away from the axis of rotation. What are we rotating it about? The x-axis. So this one is further away. Also think like when we did the curves, the area between two curves, we did top minus bottom. Think the top one. I don't want to always say top one because tomorrow we might have the bottom one is further from the axis of rotation. So that's how we describe it. Did anybody get an answer yet? We working? 0.37. Anyone? 8.37. 12. Let's see. What is 8 pi over 3? Is that the same thing? Because this comes out to be 8/3. So 8 pi over 3, or what's your decimal?
8.378.
Okay. Okay, last one. Okay, so we're going to take the same concept, but now we're going to rotate it this way. So now it's like a cone with a rounded portion scooped out. Will it be the same volume? Not necessarily, no. It could be, but let's see. So if this is y equals 1/2 x, then x is equal to 2y. So anytime it's rotated now about the y-axis, we want everything in terms of y, including the limits of integration. The top curve was y equals root x, so this implies x equals y squared. Now, what's big R and what's little r?
Oh,
Which-
right to left.
Right to left. Which one is further from the axis of rotation? To y.
That was confusing because when we drew the new one, it's technically that's also right.
Okay, that's why I said be careful thinking right to left. Think big R is the one further from the axis of rotation. But also think of the original. Don't look at my other side here. So this one's y squared. And then the volume is going to be pi. What are my limits of integration? 0 to 2. Because this ordered pair here was going to be the 0.42. But I always want to use y values for everything. So we'll have 2y squared minus y squared squared. What? Question? You're good? So let's see. So this will be 4y squared minus y to the 4th. So 4y cubed over 3 minus y to the 5th over 5. Oh no, I printed out the solutions and I didn't put an answer in there. So, oh.
I got 13.40.
13 point.
I can confirm.
404. I don't know. Do we need more than just the two of them?
They
Oh.
lost their credibility.
That's true.
Whew. Okay. We got there. Good job. Yes, we need a round of applause there. Okay, so
It's gonna be so hard now.
I'm scared. It's gonna be like
bonus, you are welcome to come back. We can tackle some of those problems together. Okay, well, tomorrow we're going to continue.
Miss Casey, tomorrow?